So now we're in chapter 3, matter and energy. So we talked about this before. Matter is everything that has uh, volume and mass. And what we're reading toward is that everything, at least that matters for us, is made of atoms. And we have, just looking at this picture here, you can see that you have the blow up of the water molecules. You have, what is that? The carbon atoms of the graphite. So of the club there. So you have the solid graphite, the liquid water. You can see that they are, everything there is indeed made of atoms, and water is made of hydrogen and oxygen, and graphite is just made of good old carbon. So what is matter? Matter is anything that has volume and mass. So lots of matter we can see with our eyes. Some we can't see, so many gases we can't see. I can't really see the air. Well, not entirely true. If I'm in Los Angeles, I can see the air, because it's got the brown haze in it. But many things are just too small for our eyes to catch up. We can see it with magnification, though. So, generally speaking, matter that we see is made of atoms and molecules. So it can look really smooth, but it's not. So there's tiny particles called atoms, and you can have atoms bound together to form molecules, and a molecule is a stable group of atoms. So atoms are so tiny you can't see them with light, but we can image them using the scanning tunneling microscopes. You can also sometimes use atomic force microscopes too, but the book doesn't talk about that. So all matter, well, that's not entirely true. There are some other forms of matter that are not made of atoms, neutrinos, for instance, but that's kind of an exotic part of matter. So you can see here that the aluminum can that has the aluminum atoms, this is not entirely accurate. It's a metallic bond, so actually there is bonding going on, and you can take an aluminum atom off of there, and it's an element. But they are in fact sharing electrons through what's called a metallic bond. So, but other molecules here, like rubbing alcohol, isopropyl alcohol, has a group of atoms of carbon, hydrogen, and oxygen. So that is a molecule, a stable group of atoms together. In this case, like we mentioned before, isopropyl alcohol. Mentioned before about scanning tunneling microscopes, probably talked about in the previous chapter, and I won't repeat myself, but you can see that the atoms do look like little pimples on there, and that has to do with the nature of the tip. And then as it approaches it, you get signal of the atom as you come close. So NIST, someone went and did this, painstakingly did this. So here's another image, an image of a DNA molecule, DNA deoxyribonucleic acid. That is the majority of our hereditary material in cells, at least for humans, for many things. Most things, actually. There are some things that do not have DNA, retroviruses, for instance. But you can see the DNA molecule on the surface of whatever that is. It doesn't necessarily say. So common states of matter, generally speaking, there's solid, liquid, and gas. And most matter can fit this way. There's some other ones, plasma, but you can consider plasma to be similar to a gas because it behaves very similar. And water is a unique substance because we actually are pretty familiar with all three of the states of water. We're all familiar with it. Solid ice, liquid water, and water vapor, steam. So there's more. The most common ice, also known as alpha ice, there are different types of solid water ice, and they have different densities, and they can actually sink in water. So in the bottom of the ocean, for instance, there is actually a lot of solid ice, but it's not the alpha ice, because alpha ice is less dense and it floats on the surface. So here are the states of matter: solid, liquid, and gas. And solids, they have a set shape and a set volume. And you can see here the image there with the ice. And this is partially what makes alpha ice. So less dense than liquid water. It's because of that honeycomb sort of open structure, such that liquid water actually is slightly more dense than alpha ice. Liquid water, it's a little more closely together, but that is not generally how it goes. Usually the solids are more dense than the liquids. But the liquid has a set volume, it doesn't have a set shape, so the molecules are free to move, and the gas has nothing holding together. So why is this? What's going on? Well, it has to do with the attraction between the molecules. So solids, generally speaking, have relatively strong forces holding them together. And then when you raise the temperature, definition of temperature is average kinetic energy. So increasing the temperature means you increase the kinetic energy, the motion of whatever it is that you are raising the temperature of. And eventually you get to the point where there's enough energy that it can break loose from the strong solid bond, and that point is known as the melting point. And then the liquid and the matter goes around, and liquid still has an attractive force, but eventually then the liquid can break free at a high enough temperature, and that is known as the boiling point. And then the gas has it's moving so fast that there's still attraction, but it's not nearly as strong to form what was called the condensed phase. So solid and liquids are known as the condensed phase, and gases are known as the vapor phase. And generally speaking, there's much more matter in the condensed phases than the vapor phases, with a couple exceptions. You can have some exotic thing, but these are the general rules that work for most. So solids have set shape, set volume, and an example of these, alpha ice, I already mentioned, diamond, quartz, iron, metal are examples of solid matter. And there are two types of solids. There's crystalline and amorphous. So crystalline means everything is very well organized. Amorphous means it's kind of jumbled. And most things are amorphous. Crystalline solids tend to be less common, but you do see them. And like a diamond, for instance, is a very pretty crystal. You get a very nice looking diamond. That's a nice pretty crystal. And iron, if you have plain old iron just sitting there, it's going to be an amorphous solid. You can make crystalline iron. I've worked with crystalline iron and with some research, but it's difficult to make. So it is very difficult to make. So some examples of this I already mentioned. And amorphous, it's much more rare to find crystalline than amorphous. Almost everything is. Glass, well, glass is an interesting case, though. Glass is kind of like a liquid that has a very high viscosity. So rubber, plastic, so it has no sort of overall order. It's just kind of jumbled together. So majority of things, like I said, are amorphous, things being solids. So crystalline solids, so sodium chloride is an example of a crystalline solid. So if you look at salt crystals, and you can see salt crystals. You can see them like with a magnifying glass, or you can buy big ones, and they are really pretty. Halite is the name of the mineral. It's really pretty, and that has a very set structure, crystalline structure. Liquid, generally speaking, liquid there's not a set form, but there is a set volume, and but the molecules move around each other. This is mostly true that if you increase the temperature, the liquids tend to expand. So you might notice that a little bit that and when temperature goes up, the liquids will expand a little bit, but it just really depends. Liquid water, for instance, is densest at 4 degrees Celsius. So gasoline, alcohol, mercury, these are examples of liquid water at this temperature and pressure. So at standard or close to standard temperature, at colloquial temperatures and pressures. So now going on the vapor phase, there is less attraction. Relatively speaking, it's just the attraction of the molecules between them is not strong enough to form anything. So gases, just kind of the particles, whatever it is, they fly around, and gases are compressible. So gases take the shape and volume of their containers, right? So what is the shape and volume of the container of your tire, the gas and the air in your tire? Well, it's the shape of the tire, right? If you slash your tire, then the gas just goes and fills the room. So then now it has a new shape, new volume. It's all its container. And also with gases being compressible, if you've ever had air in your brake line, so brakes work by the fact that liquids are incompressible. So you press on the brake, and then the mechanical force of that hydraulic line carries it to the calipers and the brakes. If you have gas in the air in the brake line, if you press on the brake, then it just compresses the gas in the line. Your brakes don't work as well or not at all. So be careful with that. If you're changing your brakes, make sure you bleed your brakes. So gases are compressible. We already mentioned that. So here are some properties. Generally speaking, I've mentioned all of these before. And pure substances. So I'm going to change topics for a second. So we can either be pure substances or mixtures. So pure substances can be either atoms, or elements, or compounds. Mixtures mean you have two different types of and kinds of atoms. So start with elements. An element is something you cannot break down into simpler substances. And the ultimate particle of an element is an atom. So meaning if I take a long rod of iron and I break that rod in half because I'm super strong, and then I take that piece and I break it in half, and I take that piece, I break it in half, eventually I get to a point that I can't break that in half anymore. I mean, you could break it apart in like a particle accelerator, but if you were to break that apart, it would no longer be iron, and that ultimate particle of the element is known as an atom. So, and we will talk more and more about this with the periodic table when we get there. So helium, for instance, helium is element number 2. It's a pure substance. It's only helium atoms. It's the gas there. So this is a pure substance. So we can also have compounds. So we can have elements, things like gold, iron, helium, but we can also have compounds that have more than one elements. Water is a compound. It's made of hydrogen and oxygen, for instance. And there are many, many more compounds than there are elements. So you can think of this as sort of like the alphabet, right? So think of elements like letters in the alphabet, and think of compounds like words, right? So there's 26 letters in the English alphabet, and you can form all sorts of words with those letters. And also, when you make compounds, you can completely change the properties of the elements. So, for instance, like the word the, T, H, and E, right, forming the word the, is very different than the letter T, letter H, letter E. There's different properties. The T and the H even sound differently when they're next to each other. Same thing with elements. So there's about maybe a third of the population that's allergic to nickel, but pretty much no one is allergic to titanium. And you can also alloy nickel titanium together, and no one is really allergic to that either. So you can have nickel titanium braces that you wear on your teeth, and you're not going to get an allergic reaction to that, even if you are allergic to nickel. So that's interesting, right? So pairing nickel with titanium changes the way that it interacts. So the compounds are very different than their original elements. So water, we've already mentioned this. Water is hydrogen and oxygen compounded together. So if we have more than one type of things together, we can be a pure substance or a mixture. So if something's a pure substance, it's made of two or more different kinds of atoms that are chemically united and fixed definite proportions. So like that's also known as the law of definite proportion. So water, H2O, 2 hydrogens to 1 oxygen. That is an example of a ratio of elements. And the mixtures have different substances, but they are mixed together in variable proportions. So they're not set. So pure substances are one kind of thing, and mixtures are many types of things. So actually, pure substances can also be just plain old elements too. So pure substances are either elements or compounds. Mixtures are mixtures of elements and compounds. So it depends on how you classify them. So mixture can be heterogeneous, which means non-uniform, and homogeneous means it's uniform. So whether or not it's uniform or non-uniform, and most things are heterogeneous mixtures. So we human beings, we are heterogeneous mixtures. We have various tissues, we have various substances, and it's even blood. Blood is also a heterogeneous mixture. It has white blood cells, red blood cells, plasma, various proteins, platelets, right? There's a whole bunch of different things that are in it. But homogeneous, sometimes homogeneous, you can hear homogeneous, homogeneous, these are both proper ways of pronouncing that word. But it means uniform. So air and seawater, these are examples of mixtures. And generally speaking, we'll say in a perfect world, it is homogeneous. They're uniform. So I mean, I know that you can get murky water, the turbidity of the water, or you can get soot and smoke in the air to form a non-heterogeneous mixture. But on a perfect day, like that beautiful day on the beach there, it is homogeneous mixtures. Okay, so let's look at this forwards and backwards. So start off the left, bottom elements, and there are, right now we know of 118 elements, and the ultimate particle of the element is an atom. And you can also take these elements, these 118 elements, you can form them together to form compounds, and these compounds and elements by themselves, they are known as pure substances. You can take pure substances and you can mix them together. If they mix together and they are uniform, then that is known as a homogeneous or homogeneous mixture. And if they're non-uniform, they are heterogeneous, so non-uniform. And you can also look at this the other way. Let's pick a substance like milk, fresh milk from a cow. If you've ever seen fresh milk from a cow, you let it sit, it separates into cream and to milk. And then you can take the cream off, and you can also take the milk, and then you can do a process called homogenization to make the milk homogeneous. Pasteurize and homogenize. That's what this says on milk. And milk is made of water. It's made of calcium phosphate. It's got various proteins in it. It's got whey. It's got casein. So, right, there's other pure substances in milk, but then you can take that pure substance and you can bring it into elements and compounds, and there are no free elements in milk, at least there shouldn't be. It's all compounds. You have compounds like water, 2 hydrogens, 1 oxygen for water, proteins, which are going to be mixtures of carbon, hydrogen, nitrogen, oxygen, and so on. And we can eventually break them all down to atoms. So hopefully I've explained that forwards and backwards for you, and hopefully that makes more sense. So there is the summary of this. And let's talk about physical properties and chemical properties. So a physical property is a substance, is a property that you observe without changing the substance. And a chemical property is one that changes its composition or lack thereof. So for instance, gold is a very unreactive metal. And that is a chemical property. But looking at gold's color is yellow. You can observe its melting point. You can observe how soft it is. You can see how it conducts. Those are all physical properties. By testing them, even melting it, it's still gold, right? It hasn't turned into something else. So hopefully this makes sense. Physical property observed without changing the substance. Chemical property is one where a substance changes, or in the case of like being noble or non-reactive, does not change. So some physical properties: odor, boiling point, so all the phase changes. These are all physical property. Color, right? These things here, these are physical property. You observe them without that. I do not recommend you taste gasoline, by the way. That is not a very good thing to do. So a chemical property. Iron rusts or gold doesn't rust. Flammability is a chemical property. So, right, because when things burn, they're no longer their original substance. When you burn gasoline, it's no longer gasoline. So, various things. So, physical and chemical changes. So, when you witness changes, many changes there, and there's two types: physical change and chemical change. So, with the physical properties, the chemical properties, you can probably guess that physical changes do not change the substance. So it is still the pure substance. If you have something, you're doing experiments on it, and then you do not turn it into a new compound, then that is a physical change only. So water boiling, you can see the water molecules there. You think it's changing, but it's really still water. It's just water vapor. It's in a different state. So. And chemical changes, this is when you have atoms exchanging or not exchanging. So when you burn things here, butane, for instance, this hydrocarbon made of carbon and hydrogen will turn into combine with oxygen to form water and carbon dioxide. So flammability is a chemical change. And so state changes, these are only physical changes. So just things like the appearance. You cut or crush something. This is a physical change only. Many times there's a physical change alongside a chemical change, right? So, like I'm wearing a black T-shirt, and if you burn it, it's gonna turn kind of gray, ashy colored, right? So, it changed color. That's a physical change. Well, no, you also did a chemical change. So. These chemical reactions always happen. These are chemical changes, and you get a new substance. So hopefully you can understand the difference. Chemical changes mean there's new substance. Physical change, same substance, just one of the physical properties is altered. So appearance. Okay, we already mentioned all of these. So changes in matter, chemical changes. When a chemical change happens, it undergoes a chemical reaction. So here is a chemical equation, and you have reactants on the left, an arrow, and products on the right. So this is known as a chemical change. The stuff that starts in the beginning is a reactant. The stuff at the end is the product. So here is an example of separating a mixture just using physical changes. This is known as distillation. So you can take two things. This is very commonly how we separate things like things out in gasoline and oil to form various fuels. We can also use it to purify ethanol, and like from making beer, wine, to purify to form alcoholic spirits, for instance. So that's this is essentially the process we do, and essentially it is the process that we do. Another thing you do is filtration. So if you want to separate two things, like if you have a product that's a precipitate, so that's when it falls out of the solution, and you can put some filter paper and filter the liquid through the paper and leave the solid behind. So this is a separation of changes. So let's have a new topic, the law of conservation of mass. So in a physical chemical process, matter is neither created nor destroyed. So that is the total amount of matter is constant. So that means that the sum of the mass of the reactants, sum of the mass of the products is the same. And Lavoisier and his wife are the ones that did this. So for instance, let's say we're burning butane plus oxygen. We start off with 58 grams of butane and 208 grams of oxygen. It reacts to form 176 grams of carbon dioxide and 90 grams of water. This reaction here, you can see reactants on the left, products on the right, and the sum of the reactants is 266 grams. The sum of the products is 266 grams. The total amount of matter has not changed. So changing topics again, we do this a lot in this class. Energy. Energy means a lot of things. If you take physics, you can say it's force times the path length, or the integral of F dot ds. We will define it as the capacity to do work. So we can take that energy that we have when we can do work, right? But now we're doing other more important things than work, right? Than doing the dishes and doing some chores. We are, playing with our cell phones or something like that, right? So energy, you have lots of energy. It means you can do lots of work, and work is the physics definition. Force times a distance is the work. So pushing your box down the hall, that's work. And matter is driven in large part by energy, and understanding this energy is very, very important for chemistry and for many other things too, but certainly for chemistry. So law of conservation of energy, just like the law of conservation of matter, energy is conserved in a chemical reaction. So the total amount of energy is constant. You can change it from one form to another, but the total amount of energy stays the same. So different forms of energy, kinetic and potential energy. So kinetic energy is the energy of motion. Potential energy is stored energy. And you can store potential energy, for instance, in gravity. So, right, when you have high potential energy, then when you release that, so like that's the old physics thing where you have the teacher holds the textbook over the desk, and I said, this has potential energy, and I'm going to turn that potential energy into kinetic energy, release the book slams on the desk, wakes up everybody who's sleeping, and said, I've turned it into potential, and I've turned the potential energy into kinetic energy. So same idea with molecules, but we tend to store them in chemical potential energy, and then the temperature is the kinetic energy of the molecules and atoms and or molecules. So there's various forms of energy. Electrical energy, so if energy flow of electrical charge. Thermal energy, this is energy of motion that atoms and molecules have. Chemical energy, this is a form of potential energy, right? We eat food that's high in energy to turn that energy and food to do other things, for us to do work on ourselves, right? So that's chemical energy. It's stored energy, and like how we get our energy is from food. We don't have a primarily photosynthesis like most plants do, right? So although we humans, we do have some photosynthesis, but not very much. So the unit of energy, we typically use the word joule. A joule is a Newton meter. So the units are a Newton is a kilogram times meter per second squared. So that is a Newton, and so a joule is a kilogram meter squared divided by second squared. So that's the dimensionality of a joule, and this is the SI unit, the metric unit for energy. We also oftentimes use calorie. So a calorie is the amount of energy that it takes to increase 1 gram of water 1 degree Celsius. So there are 4.18 joules in a calorie. So a calorie is a little higher density energy unit. You might have heard of a BTU. That's a British thermal unit. That's the amount of energy it takes to increase 1 pound of water 1 degree Fahrenheit. So a BTU is even bigger than a calorie. BTUs are not typically used in science classes. So, and nutritional calories, these are known as kilocalories. You can also see them as capital C for calories, and it's 1,000. And you might have heard of kilowatt hours. So this is the electricity, and man, I wish my electricity was 12 cents per kilowatt hour. It's not even close to that. Whoever wrote this obviously doesn't live in Hawaii. So some conversion factors, we already mentioned this. And that's what a kilowatt hour is. It's a lot of energy. So let's do some conversions here. So a candy bar has 225 nutritional calories, so kilocalories. How many joules does that have? That's a pretty big candy bar. That's the big ones that you get when you go trick-or-treating in the rich neighborhoods. So you would do dimensional analysis. So 225 calories, and it's a kilocalorie. And then the conversion between joules is 4.184, and you can see the units all cancel, and you're left with So 941,000 joules. So there's that. So physical and chemical changes. So whenever they happen, they usually have an energy change. So and the analysis, I mentioned this before, you have the stored gravitational potential energy, and then when one falls, when you drop the weight, drop the book or whatever, the stored energy turns into kinetic energy. And the same idea happens with chemical energy. So higher potential energy, they can be very unstable. It depends. I mean, so food is relatively stable, right? But food, we consume it and we get energy from that. So something like trinitrotoluene, TNT, these have pretty high potential energy and is relatively unstable. So it can, this is in fact explosive. So you can get a lot of energy released from TNT and other explosives too, C4, nitroglycerin, and so on. So the trinitrotoluene will undergo quick changes in chemical potential energy, and this is why it's explosive. So and chemical reactions that release energy, this is known as exothermic. So exo means outside, exothermic. So I always think of it like skeletons. So exoskeleton, insects have exoskeletons. Their skeletons are on the outside. We humans, we have endoskeletons. Our skeletons are on the inside. So exothermic means energy, heat goes out of the system, out of the chemical reaction. And then endothermic means that the energy goes in. It means it's the inside, the energy goes down of the surroundings when in an endothermic reaction or process. So, and this is here the same idea where for exothermic, the reactants are higher potential energy than the products, and endothermic, the opposite is true. The reactants have lower energy than the products. So, and thermal energy, the definition of temperature I mentioned before is average kinetic energy. I can be more specific. It's actually average translational kinetic energy. So just so you know in the future, if you take future classes, it's translational kinetic energy. And the higher the temperature, the more the molecules and atoms and our molecules are moving in that whatever it is you have. So heat is the transfer exchange of thermal energy. So when you put something like an ice cube into hot water, the heat from the water flows to the cooler ice. So that's the other thing with heat flow. Heat always flows from hot to cold. Heat never flows from cold to hot. And that part of that is from the second law of thermodynamics. So heat will always go from hot to cold. It doesn't go the other way around. You put your frozen ice cream in the oven. You turn on your oven. The hot oven melts the ice cream. You don't the ice cream doesn't become colder and then the heats up the oven. It doesn't work like that, right? Heat flow is always from hot to cold. So, and the temperature is the measurement. It's how much the average of the kinetic energy of that is. So let's talk about the different scales. So Fahrenheit scale, this was set to be as colloquially, like it was set to be like, that brine freezes at 0 and 96 is body temperature, and this was meant to be a colloquial, normal people stuff. And water freezes at 32, water boils at 212, and room temperature is approximately 72. My room temperature right now is higher than 72. It's probably more like 80, Hawaii again. So Celsius scale. Celsius scale is based off of water. Sometimes it's referred to as centigrade. At sea level, the average pressure of 1 atmosphere, water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. And room temperature tends to be 22 degrees Celsius. Human body temperature is 37 Celsius. So the Kelvin scale, this is the absolute scale. So remember, temperature, definition of temperature is average kinetic energy. So what does it mean when something is not moving? You can't get colder than absolute zero, and that's when at absolute zero motion stops, and you say motion virtually stops. So you can still, depends on what it is that you have. You're wondering, why do you have the word virtually there? Molecules can still spin and vibrate. So the translational motion, the molecule, atoms and or molecule moving around in space-time, like moving left to right, up and down, that stops at absolute zero. But it can still spin, it can still vibrate, and even further, you can the quantum uncertainty of things. You have some uncertainty in the position of the material, so you could argue that is motion. It depends with that. So that's why you have this virtually stop. So it's kind of, it just means that it's not moving anywhere. That's translationally, it's not moving anywhere. So Kelvin scale, it's absolute zero is negative 273.15 Celsius. And so 273 water freezes, water boils 373. And 295 Kelvin is room temperature. It's going to be kind of a chilly room temperature. So that's a little chilly. It's usually warmer. So here are the different scales. So Fahrenheit, Celsius, and Kelvin. Fahrenheit actually has an absolute scale. It's called Rankine. You'll also see it as R. So there actually is an absolute Fahrenheit scale, but that's not used as frequently. But there are the different types of temperature scales there. So we can convert through Fahrenheit and Celsius by this equation here, and we use Celsius but not Kelvin. So you have to convert that different times. So if you want to convert the units this way, and if you're wondering where the Fahrenheit and Celsius join at a certain point, the value that Fahrenheit and Celsius are the same is negative 40. So negative 40 Fahrenheit is the same thing as negative 40 Celsius. So let's change topics and talk about specific heat capacity. So metals, for instance, tend to have relatively low specific heat capacity. I've noticed this. You can take something like when the sun is shining on a seatbelt and you can touch the seatbelt, it's really hot, but you can keep the heat goes away pretty quickly though on a hot, the sun shining on a seatbelt. But if you have like something like hot soup and you put hot soup in your mouth, you either have to spit it out or put some ice cubes in there, right? Because the hot soup is going to stay very hot. So water has a very high specific heat capacity, for instance. So water has a high specific heat capacity. It doesn't have the highest, but it has relatively high. And things like metals have relatively low. It's the amount of energy it takes to change the temperature. So specific heat, it's 1 gram, 1 degree Celsius. And here are various specific heats. And you can see water is all the way up there. And that's the same, you notice that's the same conversion of a joule to a calorie is the 4.18. That's where we get it from. And like I said, there's higher specific heat capacities than water, but water is just particularly high. And but water absorbs a lot of heat, or it releases a lot of heat, and the temperature doesn't change very much. So let's use this an equation here. So heat flow is going to be mass times the specific heat capacity times the change in temperature. And so what happens to the temperature change? Also, another fine point, units, the unit degrees Celsius and the unit Kelvin, they are the same unit. So when you have a temperature change of 5 degrees Celsius, you also have a temperature change of 5 Kelvin. So if you look at these units up somewhere else and you see in kelvins, a Kelvin and a degree Celsius, unit-wise, you can use the same units. So in terms of different, the magnitude of the scales is different, but the mathematical value of the variable is the same. And that's important for division and multiplication. So here's the equation. Q heat is mass times specific heat capacity times change in temperature. And let's apply this equation to this problem. So gallium is a solid at room temperature. It melts at 29.9 degrees Celsius. And if you hold gallium in your hand, it will melt. So how much heat must 2.5 grams of gallium absorb from your hand to raise the temperature from 25 to 29.9 degrees Celsius? And there is the specific heat capacity of gallium. So we're going to use the equation, and Q equals mc delta T. And we know the mass of the gallium, we know the initial temperature, we know the final temperature, and we know the specific heat capacity. And find the heat flow. So Q is the heat flow. So something with delta T, delta is always final minus the initial. So when you do this and figure out the change is always final minus the initial. So right, so think of money. If I start out the day with $100 and I end the day with $50, what is my change in money? It's the final minus initial. It's 50 minus 100, that's negative 50. My delta of dollars is negative 50, right? So same thing with temperature, final minus the initial, and in this case here, the heat flow is positive. So you have a delta T of 4.9 degrees Celsius, and the Q equals M, specific heat mass, specific heat capacity times change in temperature, and we get 4.6 joules doing this. And I notice one thing I've mentioned, I keep on saying heat flow and direction. Negative heat flow means it's leaving the system. Positive heat flow goes into the system. In this case, the system is the gallium metal. So the gallium metal is absorbing energy. Your hand, actually, if you wanted to follow, like what is the heat flow of the hand, it's going to be negative 4.6 joules. So review of this. Matter is something that has mass and volume. It can be a solid, liquid, or gas. Solids can be amorphous, which means random patterns, or crystalline, which means set patterns. Pure substances can be elements or compounds. And you can take two or more pure substances to form mixtures. If the mixture is uniform, it's homogeneous or homogeneous. If it's non-uniform, it's heterogeneous. And talking about physical properties you observe without changing the substance. Chemical properties involve the change of the substance. Physical change, only the appearance. The composition does not change. Chemical changes, the matter change, the atoms exchange. So atoms exchange and a chemical change. Law of conservation of mass says matter is not created or destroyed. Law of conservation of energy. Energy is neither created nor destroyed. So, and we have some units of energies. We talked about the joule. We talked about the calorie, both little calorie and nutritional calorie, and briefly mentioned kilowatt hour. So, chemical reactions that release energy are known as exothermic, meaning heat leaves the system. Those that absorb energy are known as endothermic, which means heat goes into the system. And temperature is the average kinetic energy of the atoms in our molecules. We have the different scales, and we also have specific heat capacity. This means that the higher the heat capacity, the more energy it takes to change the temperature of the substance. And water has a relatively high heat capacity. Metals have relatively low heat capacities, for instance. So here are the learning objectives and the copyright. Thank you, and see you next time.